Yes, the next scheme of classification is on the basis of thermal response, response to high temperature, low temperature, how the polymers behave. The two major classes are thermoplastics and thermosetting, thermoplastic polymers and thermosetting polymers. You have seen the examples of synthetic polymers, semi-synthetic polymers and natural polymers. All of them can be categorized into these two classes, thermoplastic polymers and thermosetting polymers. Thermoplastic polymers are those which softens on application of heat, again hardens on cooling. This is a reversible change. If a polymer shows reversible change from soft to hard, hard to soft by heating and cooling and vice versa, we get thermoplastic response. Polyethylene, polypropylene, polyesters, of course saturated polyesters, polyamides, polycarbonates, polystyrenes, nylons, polyacrylates, polyurethanes. These are all thermoplastic polymers. These polymers are recyclable. Once a product is made from these thermoplastic polymers, after use of the polymer, when it is disposed, it can be managed by collecting those disposed polymer. After cleaning, washing, drying, again those polymers can be reprocessed for making a new set of products known as recycling or recycled products. So, thermoplastics can respond to recycling of waste plastic, waste polymers, whereas thermoset polymers behave differently. You have seen in case of that phenol formaldehyde resin synthesis, urea formaldehyde resin synthesis, melamine formaldehyde resin synthesis, there you saw that these polymers initially remains in thermoplastic stage, linear, then when it is branched still it is in the thermoplastic stage, but on further heating that leads to a stage C polymer or C stage polymer which are thermoset, means this is a irreversible change. These thermoset polymers are infusible by heating, it cannot be fused, cannot be melted by heating, and they are also insoluble in any solvents because of a 3-dimensional network of polymer molecules. They form a 3-dimensional network of polymer chains. That is why these polymers are insoluble and infusible, because in order to make them fusible, meltable or soluble, these intermolecular bonds are to be broken, whereas thermoplastic molecules are polymers are linear molecules. Examples again may be large, only few examples are shown over here. Epoxide polymers, epoxy polymers, phenolic polymers, polyamide resins can lead to thermoset also, in addition to thermoplastics. Polyesters, you can have thermoplastic polyester, whereas in you can have thermoset polyesters also. If you take unsaturated polyester, then unsaturated polyester undergo intermolecular cross linking reaction to form a 3-dimensional network of polymer chains which is insoluble and infusible. Say if you take example of cellulose, cotton. Now, we have got the definition of thermoplastic and thermoset polymers, linear polymers, branched polymers and cross linked polymers, 3-dimensional network polymers. Now, if I ask you a question, what about cellulose, cotton, is it soluble in water? Have you found have you seen any solvent for cellulose, cotton? No. So, we can call it thermoset polymer. Can you melt cotton? You can melt polyester fiber. Can you melt cotton? Why? The question is why? We cannot melt cotton. We cannot dissolve cotton. Why? There must be some reason. What is that reason? Can anybody answer? Any of you? Ready? From common sense you can answer. Yes? I am not getting. What kind of 3D network? Through primary bond? Primary bond. Sorry, you are wrong. Cellulose is a thermoplastic polymer, cotton is a thermoplastic polymer, but it cannot be dissolved in solvent, it cannot be melted. While if you want to melt it by heating, it will degrade because of extensive hydrogen bonding between hydroxyl groups of anhydroglucose units. There are 3 hydroxyl groups in anhydroglucose unit. Cotton cellulose is a polymer of anhydroglucose ring containing 3 hydroxyl groups, 1 primary hydroxyl group and 2 secondary hydroxyl groups. Please look at the cellulose molecular structure, and that enter into extensive intermolecular hydrogen bonding. Now, the chemical bonding aspect is coming, you see. Here you can compare discrete molecular compounds with the polymeric compounds, polymeric materials. You have to think of primary bond and secondary bonds. What are primary bonds? Primary bonds can be covalent, ionic, coordinate covalent bond, metallic bond. Secondary bond, hydrogen bonding, van der Waals bonding. What is the genesis of van der Waals bonding? Difference in electronegativity between atoms. That is an induced effect. So, think of ethylene, it is gas at ambient condition, is not it? Ethylene is a gas, and when ethylene is converted to polyethylene, it becomes a tough, hard, solid plastic material. Where from this strength has come? It is van der Waals bond. London dispersion force. London dispersion force that constitute these van der Waals bonds, whose magnitude is around 1 to 3 kilocalories per mole. Hydrogen bond 1 to 5 kilocalories per mole. Bond energy. So, here this hydrogen bond, huge hydrogen bonding is there, intermolecular hydrogen bonding is there. So, it is insoluble. Then next category is polymers can be of 2 types, condensation polymers and addition chain polymers based on the principle of formation. Now, ethylene when converted to polyethylene, it is made by addition chain reaction. I was talking about functional groups. In ethylene, there is no such functional groups as is found in case of diacid, dialcohols, diols, diamines. That means, there is no amine hydroxyl acid functional groups available in ethylene molecule, but it undergoes polymerization to form polyethylene. Where is that bond? What is that functional groups then? The pi bond, that pi electrons. That pi bond opens up by homolytic cleavage into 2 free electrons on each carbon, and that those free electrons help in combining with one another, forming the polyethylene molecule. that is addition chain polymerization. So, all these polymers, all the monomers having olefinic double bond can undergo addition chain polymerization, or ring monomers can also undergo addition chain polymerization. As condensation polymerization that needs functional groups like hydroxyl group, carboxyl group, amine groups or acetyl groups, acyl groups like this, that condenses to form a polymer chain eliminating a small molecule of, say, it may be water, it may be hydrogen chloride, it may be sodium chloride, depending on the functional groups which have been reacted to form this polymer. So, we can have addition and condensation polymers. So, if you look into the synthesis of polyester, if you look into the synthesis of polyamide, if you look into the synthesis of polyimides, if you look into the synthesis of phenol formaldehyde, phenol and formaldehyde reaction product, polycarbonate synthesis, epoxy resin synthesis, you will find that some small molecule is eliminated, and that means this is a condensation reaction. And this condensation reaction occurs in steps, multi-step reaction. Step 1, forming a dimer. So, various steps. So, it is a slow process. First a dimer is formed, a trimer is formed, tetramer is formed, pentamer is formed, hexamer is formed, heptamer is formed, octamer is formed, nonamer is formed, dodecamer is formed. This way it proceeds in steps, and these are called intermediates. In each and every step there is a condensation reaction between two functional groups, either one hydroxyl group and a carboxyl group, or carboxyl group or amino group, like this. Okay. And slowly these intermediates grow in length, in bigger and bigger and bigger and bigger. So, this is a slow process. Condensation polymerization is a slow process, whereas addition chain polymerization is a very fast process. Once a monomer is initiated by opening a pi bond, eventually it finishes its growth to a very big molecular weight, molecular size polymer. Say time taken for completion or formation of one addition chain polymer may be fraction of a second, say 10 to the power minus 7 second time. 10 to the power minus 7 second time a polymer molecule is formed in case of addition chain polymer, whereas step polymers it takes hours of time. Okay. So, now you can you understand the examples of these polymers, addition, what are the addition chain polymers, what are the condensation polymers, you understand from this thing. Example, you can get the examples. The synthesis principles. I have already told what is addition chain, addition polymers, examples polyethylene, polypropylene, polyphenol chloride, polymethyl methacrylate, polystyrene, polyacrylates, styrene butadiene rubber, polybutadiene rubber, chlorophene rubber, all these are made by addition chain polymerization principle, and condensation polymerization principle done by condensation reaction between reactive functional groups of monomers. Examples are polyesters, say polyethylene terephthalate, nylons, polyamides, polycarbonates, epoxies, phenolics, urea formaldehyde resin, melamine formaldehyde resins, that means aminoplasts, polymers, etc. Then classification on the basis of line structure. The polymer can be of linear structure, branch structure and cross-linked polymers. You have seen, I have already explained what are the classes of polymers: linear polymer, branched polymer and cross-linked polymers. For example, polyethylene, if you take the polyethylene example, polyethylene, I told you LDPE and HDPE, two grades. For example, the low density, high density, this is a branched polymer, this is linear polymer. There may be very short branches or very some sort of branches is there, but in general you can say, we can say that LDPE is branched. Because of this branch, it is of low density. Have you got the concept of low density due to having branch? Low density means what? Packing. Packing efficiency. Now, if there are branches, then that branch will hinder closure approach of the neighboring molecules. You have cut your hair. Now, how do you feel if you place your thumb over here? Is it not pricking your skin? Place your, is it not pricking your skin? No, you are wrong. You ask your friend to touch. It is pricking.
Yes, sir.
Now, as this hairs grows bigger and bigger and bigger, it will become comfortable. Actually, my teacher, he used to tell a story like this. There was a student in the class, say named Raghu. Every day he used to come to the class without preparing lesson, and teachers become very angry. Why you have not come prepared with your lesson every day? So, you are not studying, you will not be able to do good result in the exam. So, you must study and come to the class every day. The same thing is happening, and since the teacher becomes angry, he used to hold his hair like this, give a shaking on the head. That means, every next day he was just expecting that if gives this kind of some your pain to the student, the next day he will come preparing his lesson, but no result. But on this contrary, the student also, he was getting angry. Sir, well, next day I will give you a lesson, I will teach you a lesson. So, he came cutting his hair like that. So, he could not hold his hair. So, days onwards, so he got pricking. The teacher, he just give just after touching, he was getting a shock like. So, again the teacher was like, oh well, you have taken this kind of measure. Well, let me wait for a few days, and again your hair will grow, and then I will be able to catch like that. So, this is a case of branching, and you see effect of branch. So, if there is the length of branch is longer, then the effect on density is minimum. If the length of branch is shorter, effect of density is there, on more on density is more. So, this is the situation. So, low density you understand, So, low density polyethylene, how it is made? Actually, low density polyethylene, it is a copolymer of ethylene and one hexene or one pentene. So, this you will have 4 or 5 carbon atom branch, is a regulated polymer chain structure in order to develop low density polymer for making films or very low profile products, whereas high density polymer there is no such branches. Okay. And this linear polymers can also be cross linked. Say if you take polyethylene, use some peroxide, sorry, DCP, cross linked polyethylene, XLP, vulcanized rubber, cis-1,4 polyisoprene is a thermoplastic polymer. Hevia tree, from Hevia tree you get latex, we coagulate the latex, isolate the solid rubber, wash it and dry, we get dry rubber, that is thermoplastic. When you add sulfur to it along with other chemicals, auxiliary chemicals, we get cross linked vulcanized rubber. It is a tire, it is a vulcanized rubber. Ebonite, it is a rubber. Vulcanized rubber, natural rubber plus 35% sulfur, ebonite, used in making battery case. Ebonite is a vulcanized rubber used for making battery casing, battery container, storage batteries. This is schematic representation of, this is a linear polymer, this is branch polymer, branches can be of different types, long branch, short branch like this, and C is a planar network structure configuration, and this is a 3-dimensional network polymer or known as space network polymer. Reinforced concrete, that is also a 3-dimensional network structure, although that is not a polymer, but the concept comes from there, 3-dimensional network polymer. Now, if I ask you a question, now here you see in case of linear polymer, there is a limit of molecular weight, its length is from here to here, it may be say 1000 kilodalton or 10 kilodalton, 100 kilodalton, like this. Here molecular weight is little bigger because of these branches, here molecular weight is little bigger. And what is the molecular weight of this system? Cross-linked system, this one, 3-dimensional network system. Who can say what would be the molecular weight of this 3-dimensional space network polymer system? Is there anybody to answer? Is this molecular size finite? Is this molecular size finite? Yes or no? Is this finite? Is this also finite? Huh? Infinite. On cross linking, intermolecular linkage of linear molecules lead to infinite molecular weight, infinite molecular size. Then classification is application and physical properties, rubber, plastics and fiber. A same polymer can be available in any of these three different forms, either plastic or fiber or rubber. You take polyethylene, you can have polyethylene plastic, you can have polyethylene fiber, you can have polyethylene rubber. What is the difference among these three? The difference is the matter of degree of alignment. It is a matter of degree of degree, extent of alignment, molecular alignment, molecular order, molecular organization. If the organization is highest, it will lead to a fiber. Suppose this is one molecule, this is another molecule. If they remain side by side laterally this way and there is contact with each other, so this is very strong, but if the orientation is like this, only contact in one point. So, this is in aligned, maximum aligned stage, aligned situation, minimum aligned situation. So, molecular segmental order, alignment, crystalline alignment, crystallinity. So, fibers are maximum crystalline than plastics. And elastomers, minimum crystallinity, minimum or no crystalline order, amorphous. So, from the degree of alignment, from the concept of molecular order, we can categorize polymers as rubbers, amorphous, fibers, maximum crystalline, and plastics, intermediate crystallinity. Well, tacticity, disposition of side groups in space. Through that disposition, we get three different geometric configurations: isotactic configuration, syndiotactic configuration, and atactic configuration. Then, what are the examples of polymers which can show such type of configurations? Can this polymer show such type of configuration? No, because this is symmetric. This molecule, this is non-symmetric, means there is some asymmetric center. This center is asymmetric, known as chiral center. That means each and every carbon is different from others. So, this leads to such type of isotactic, syndiotactic and atactic configurations. So, this way polypropylene, polystyrene, PMMA, polyvinyl alcohol, polyacrylates, polyacrylic acid, This can lead to this tactic configuration, tactic structure or tacticity. Now, before the discovery of Ziegler-Natta catalyst, you know, have you heard this name, Ziegler and Natta? Yes. Organometallic catalyst, they developed this catalyst and for which they won Nobel Prize in 1963. Based on their work, technology was developed in 1970s for preparing this polyethylene, polypropylene using stereospecific organometallic catalyst for stereospecific polymerization, say isotactic polyethylene, polypropylene or syntactic polyethylene. Prior to development of this technology, when polypropylene was manufactured, around 30 to 40% of the product became atactic. Then what is atactic, what is isotactic, what is syntactic? Look at this structure. Here you see this is one configuration, this is another configuration, this is another configurations. Now, these two configurations are symmetric configurations. This is isotactic, if this is isotactic, this is syntactic configuration, and here you see there is no symmetry, there is no regularity in disposition of the side groups, this one. So, this is atactic configuration. Now, atactic polypropylene is a useless product. It is a sticky, soft, weak polymeric mass, waxy mass. No product can be made from this atactic polypropylene, whereas isotactic and syntactic polypropylene is strong and tough polymer. So, 30 to 40% of atactic propylene would have to be separated from this isotactic or syntactic polymers, and that was a loss, and because of that reason the cost of polypropylene was very high. Now, that cost was reduced to a large extent using this stereospecific catalyst, say aluminum alkyl and titanium tetrachloride combination, titanium tetrachloride and aluminum alkyl or titanium tetrabromide and aluminum alkyl. This combination, organometallic combination, leads to 100% conversion to either syntactic or isotactic with no atactic variety. So, today the cost of polypropylene is very low, is the lowest cost polymer, cheapest polymer available in the market as commodity polymer. Okay, it is a commodity polymer. A commodity polymer is such which is available at low cost if it finds large volume consumption for making products. These are known as commodity product for general purpose use, polypropylene or polyethylene. This is also a commodity polymer. Polyethylene, polypropylene, polyvinyl chloride, these are the three polymers, three polymeric members which are used most among all other products available. Crystallinity, I told you, amorphous, semi-crystalline and crystalline polymers. Now, this crystallinity or concept of crystalline structure in polymers are little different from the concept of crystallinity in metals and in other discrete molecules. In metals and discrete molecules, find crystalline, if we say crystallinity, crystalline, that is 100% crystalline material with little defect. But polymers, although we call it crystalline polymer, but the crystallinity, percent crystallinity is not 100, it is less than that. It may be 60%, it may be 40%, it may be 50%, it may be 20%, like this. What is this? That means, there are certain zones or domains in a polymeric sample having crystalline region, crystalline order followed by amorphous regions. So, it may look like this. these are crystalline regions. That means, one molecule can pass through amorphous regions to crystalline regions, through crystalline regions to another amorphous regions. So, these are known as crystallites. Actually, this is a fringed model, fringed bicyclic model, where crystallites remain dispersed in amorphous matrix. It is semi-crystalline or quasi-crystalline polymer. Now, this is the schematic representation of unoriented melt, this portion, unoriented melt, polymer melt. If you melt it, it looks like this, zigzag, zigzag. That means, there is segments, polymer segments are folded, coiled, in folded and coiled configuration. I have taken this from a book for your understanding, that is Science and Technology of Polymers, Plastics, Rubbers and Fibers, written by Professor P. Ghosh. That day I told you to buy this book, and this figure is oriented, cold drawn from melt. If you heat a polymer towards melting, then if you apply some stretching force, molecules gets aligned, it becomes crystalline. So, this is more crystalline than this one. This is amorphous, this is crystalline. Structure property relationship. Why this is necessary? Because you have to look into the polymer structure, then correlate the structure with the properties. If you want to make a product, for selection of a suitable polymer, then you must know the properties. Then if you have to make a correlation between the properties with the molecular formula, chemical formula of the polymer, structure of the polymer. So, there are few points: molecular weight, you have to know the molecular weight, you have to know the linearity or non-linearity of the polymer chains, molar cohesion, secondary valence forces, secondary bonds, polarity in the molecule, crystallinity, then effect of temperature on the polymer sample, how it behaves, then deformation behavior of the polymer under load in amorphous condition, amorphous state, in crystalline state, then on application of temperature, heat. That means, if you change the temperature of the polymer, then there are certain transitions of phase from glassy to rubbery phase to melt phase, glass transition, melting transition, and then property. Based on these structural features, you know the properties of the polymer, which can be exploited for end use of the polymer for making products. Well, let us stop here. Next day we will see. Thank you.